limited to b, because all I've done is multiplied xa of t times this impulse train to give me xs of t. So this, as I've drawn it, is xs of omega. So when you multiply by an impulse train, you get another impulse train that's got areas that has areas that are equal to the samples of xa of t every capital T seconds. And the Fourier transform of that impulse train is this periodic spectrum, which is periodic with period 2 pi over capital T. Now the last step is to convert the time axis from every t seconds to every integer value, x of n. We lose the whole notion of capital T. So you can think of this process of mapping impulses to samples as dividing the time axis by capital T. Well, if I divide the time axis by capital T, then in some sense I need to normalize the frequency axis by 1 over t. And that's exactly what happens. The mathematical equivalent to replacing impulses every capital T seconds to discrete time samples every integer is a rescaling of this axis along the relation omega equals omega capital T. So now instead of having these spectral limits be b, I now have bt and minus bt, and instead of being periodic with period 2 pi over t, it's now periodic with period 2 pi. And that gives us the same spectrum exactly as we got before. We have the same relation in the range minus pi to pi. We have a scaled by 1 over t and stretched by capital T version of the original spectrum. But we've just interpreted it now through this two-step process of taking the analog signal first multiplying it by a periodic impulse train with impulses every capital T seconds to give us this discrete signal xs of t. Although it's discrete in the sense that it's an impulse train, it still has a notion of the time axis, 0t, 2t, 3t, and so forth. And then it has a spectrum which is periodic with period 2 pi over capital T. We then take that continuous time signal that's all comprised of impulses, and we exchange those time domain impulses to discrete time domain samples by rescaling the time axis by capital T, which rescales the frequency axis by capital T to give us the spectrum. So that two-step process, of multiplication by an impulse train and then converting impulses to samples has two components. The first component takes the original spectrum of xa of t. This part, the periodic sampling, periodic impulse train sampling, gives rise to periodic replication of xa of omega every 2 pi over t. And then this process of turning continuous time impulses to samples in discrete time replaces the time axis, or let's say it rescales the time axis, by capital T. So therefore, it must also rescale the frequency axis by 1 over t. And that's what gives us the periodic spectrum rescaled by 1 over t. The scaling in amplitude by 1 over t that we get comes from the area of the impulse train. This impulse train corresponds to an impulse train that has areas that are 1 over t in hertz or 2 pi over t in radians. So this maps everything that was in the range minus pi over t to pi over t to now be in the range minus pi to pi. Okay, so now let's put some of these things together. If I have an analog signal XAFT and I sample it with an ideal continuous to discrete converter to give me the discrete time signal x of n, then if I then take those samples and I process them with an ideal discrete to continuous converter at rate capital T to produce analog signal YA of t, then I would hope that YA of t gives me back XA of t if I haven't done any processing to those samples and if the original signal was band limited to plus or minus pi over capital T. So what I need to do now is think about what goes on inside this ideal discrete to continuous converter. So just like before, I'm going to think of this as a two-stage process that sort of undoes the steps that we had before. The first step is I'm going to exchange discrete time impulses for continuous time impulses. So this is a time change. And those impulses are now going to be clocked out at every capital T seconds. And then I'm going to take the output and filter it with some continuous time filter with frequency response g of omega. So this first step, again, this isn't how a real discrete to analog converter would operate, but mathematically it breaks the process into two steps, which is convenient for us. So if I start, let's just go through this set of mathematical operations. If I start and exchange the discrete time samples x of n for an impulse train, I'm basically going back from x of n to x of s of t. So I'm going back from this spectrum that's discrete, the discrete time Fourier transform, which is periodic with period 2 pi in little omega, and I'm going back to this signal, which has a Fourier transform in capital omega that's periodic with period 2 pi over capital T. So I'm rescaling the time axis back by capital T, which rescales the frequency axis back by capital T. So this operation basically just takes me from being periodic with period 2 pi to having exactly the same spectrum, but now being periodic with period 2 pi over capital T. So if I have x of n and it's got discrete time Fourier transform, a slightly different picture this time.